When two light atoms, for example hydrogen atoms, join together, the laws of physics tell us that a large amount of energy will be released. But the experiments performed so far by scientists to achieve nuclear fusion have always yielded a lot less energy than the inputs. This week, the Lawrence Livermore National Laboratory in California, which uses an approach called inertial confinement fusion, announced that they achieved a huge improvement in the record energy yield from a fusion experiment. I'm Jacopo Russo, and I asked Debbie Callahan, a lead researcher on the project, to describe what the experiment looks like.
So what we do in inertial confinement fusion is we take our fusion fuel and we put that into a small sphere that we call a capsule. And that sphere is made of diamond or high density carbon, we'll sometimes say. And what we want to do is ablate the outside of that capsule, and then it forms a spherical rocket, which will then implode on itself and bring that fuel to high density and temperature. That's what's needed to get to fusion.
Okay, a spherical rocket that implodes on itself. That sounds very cool already. So, how do you ablate? How do you destroy this spherical capsule?
So, in order to ablate the outside of that capsule, we're going to use a very large laser, the National Ignition Facility laser. The laser facility is the size of 3 American football fields. So, you can kind of picture how big
What?
that is.
Are you
It's
serious?
huge. And it actually has, it's not just one laser, it actually has 192 laser beams. We then take those 192 laser beams and we focus them down into a little cavity that we call a hohlraum. You can picture it, it's just a little cylinder that's made of gold, and it has a little hole at the top and the bottom, and the laser beams enter 96 beams from the top, 96 beams from the bottom. When those laser beams strike the inside of the hohlraum, they generate X-rays, and those X-rays are what we're going to use to drive the capsule. Basically the hohlraum is like a little X-ray oven.
How big is the hohlraum and the capsule you talked about?
So the hohlraum is about a centimeter long, and then the capsule is about 1 millimeter in radius.
That's incredible. So you need 3 football fields worth of laser to shoot energy at a 1 millimeter tiny capsule with your atoms inside that you want to fuse.
Yes, exactly, because we're trying to put a lot of energy into a very small amount of matter.
What was so special about your latest achievement?
For the first time, we actually got our implosion, that hot, dense core, to ignite and for the burn from the fusion to actually propagate out into the surrounding shell. That resulted in a much larger amount of fusion energy coming out of the system than we'd ever gotten before. We got almost 6 times the amount of energy that we put into the capsule, the little sphere in the center, and about 70% of the laser energy that we put into the hohlraum. So this is a big deal.
Because the main problem with fusion at the moment is that you need to put in more energy than the energy you get out. And that's
Exactly.
if you count the energy that comes from the lasers, and then I suppose there will be some losses.
Exactly.
How much energy did you produce?
We produced 1.35 megajoules of energy. The laser energy we put in was 1.9 megajoules. So that's about 70% of the laser energy.
I'm trying to think how much energy that is. You see sometimes at the back of food packages, right? You see joules and
Right.
kilocalories, right?
Yeah, it's not actually that much energy. I think people make analogies to, candy bars.
It's a snicker of
It's
energy.
something like a Snickers bar. But the important thing is that it's in a very short time.
It's easy to split atoms apart. We do that every day in nuclear plants around the world to make energy. Why is it so hard to make atoms join?
Well, if you think about it, you have 2 positively charged nuclei. They want to repel each other. They don't want to go together. And so it takes a high pressure, high temperature, high density in order to force that to happen. So that happens in the sun and the stars because they're very large and they have gravity holding them together. So, essentially we're trying to make a little star in our facility.
You're trying to make a little star with a laser that is 3 football fields long.
Yes.
What advances made this achievement possible? What went right this time?
The big change for this one was actually we made the capsule a little bit larger, but that's challenging because our laser didn't get any bigger. And so we had to figure out how to compress a larger capsule, but with the same amount of laser energy.
Do we have more powerful lasers today? Would that help?
Really, what we need is more energy in the laser, and NIF is the most energetic laser, the biggest laser in the world. There are potential ways to make NIF produce more energy. Our team is working on that now. We're, of course, going to try to improve on that design. We've got several experiments planned in the next year or so to try to get a higher yield out of it.